welcome to this explainer. Today, we're tackling something literally every single student encounters, but so many just deeply misunderstand. I'm talking about measurement. Too often measuring gets reduced to rote memorization, just memorizing formulas or rules without having any real idea why they work. And that's exactly why we're diving into a developmental, student-centered approach to building these measurement concepts from the ground up.
Here is our roadmap for today. First, we'll unpack the process of measuring. Then, the power of estimation. Third, length, area, and volume. Fourth, time, money, and angles. And finally, we'll cover overcoming student misconceptions.
Section 1. The process of measuring. Okay, let's trace the learner's journey from a really messy physical concept all the way to an abstract formula. Look, the reality here is actually pretty stark. And AEP data shows that US students struggle with measurement more than almost any other math topic. Faced with a ruler, a lot of students will just count the tick marks without having any idea why they're counting them or what those marks even represent. They're just completely lacking that foundational conceptual understanding of what measurement actually is.
So how do we fix this? Well, let's walk through a totally crucial three-step instructional sequence. Step 1. You have to decide on the attribute to be measured. You need to physically decide if you're measuring the height, the weight, or maybe the volume of a bucket before you do literally anything else. Step 2. Select a unit that has that exact same attribute. And Step 3. Compare the units to the object by filling, covering, or matching. The big takeaway here, notice that we do not jump straight to tools. There's a really stark contrast between non-standard and standard units. Jumping straight to standard units like inches or centimeters honestly just confuses children. Instead, starting with non-standard, improvised units is the way to go. Like using index cards to cover a desk, or lining up straws to measure a line. Sure, it's messy, but it is highly conceptual. It forces the student to focus on the actual attribute being measured, and once they get that, then we can introduce the efficiency and abstraction of standard units, like rulers and standard formulas.
Section 2. The power of estimation.
Approximation is a practical skill we use almost every single day, right? But estimation shouldn't just be a random guess. It needs to be a dynamic physical process. Let's look at 3 highly effective estimation strategies you can use in the classroom. First, develop personal benchmarks. Think about using your own stride or knowing your hand span is, say, about 10 centimeters. Second, use chunking. If you're estimating the length of a room, mentally subdivide it using the windows or bulletin boards as manageable chunks. Third, iterate units mentally or physically, like actually marking off a length using your hands to keep track as you go.
But here is a massive trap that so many educators fall into. Do not promote a winning estimate. It discourages estimation and promotes only seeking the exact answer. This is absolutely vital. When you challenge that traditional grading mindset and create a competition for the best estimate, you completely ruin the intrinsic motivation of estimating. You're basically teaching students that estimation is just a flawed way of getting the right answer rather than a valuable reasoning tool all on its own. Just accept a reasonable range instead.
Section 3. Length, area, and volume.
To see how these spatial concepts connect, let's start with length. When we look at measuring something simple, like a crown with a ruler, we hit a really foundational point. Students absolutely must learn to iterate and count the actual spaces or the physical units themselves, not just the tick marks, not just the numbers. If they just count lines, they aren't actually measuring. They're literally just reading symbols. The physical spaces between those lines are the actual units of measure.
Building right off length, we move into the second dimension. Area is defined conceptually as the two-dimensional space inside a region. We have to define area conceptually by having students physically cover surfaces with squares or tiles. If we do this, we can finally stop students from confusing area with perimeter. When they actually physically cover a space, they experience a true aha moment. They realize, oh, I'm measuring the inside, not the boundary.
So, a super crucial point here is how we actually teach the area formula. We really need to shift away from teaching area equals length times width. Instead, teach area equals base times height. Why is shifting to base times height such a game changer? Because it naturally generalizes to other shapes. If you know base times height, you don't just know rectangles anymore. You know parallelograms, and you can easily figure out triangles. It just completely unifies the geometry concepts.
Now, see how this builds seamlessly right into the third dimension, volume. As the formula states, V equals A times H. By connecting the area formula directly to the volume formula, we're proving to students that mathematics actually makes sense and builds on itself.
You find the area of the base, that one single flat layer, and you just multiply it by the height to see how many of those layers fit inside the box. It is the exact same conceptual logic.
Section 4. Time, money, and angles. Let's apply these foundational concepts to everyday life, starting with time. Time is incredibly tricky for learners because it's not a physical object you can hold in your hand. But using an empty timeline for elapsed time brilliantly solves all that cognitive heavy lifting. Instead of relying on really confusing clock arithmetic where base 60 suddenly meets base 10, students can physically jump along the empty timeline, marking hours and minutes in a way that just makes logical, visual sense.
Next up is money. We really need to highlight the crucial takeaway that coin value lessons must focus on purchase power, the idea that a dime buys the exact same thing that 10 pennies can buy. Teaching money has to focus on abstract purchase power rather than just counting physical objects. Because think about it, a dime is physically smaller than a penny, but it's worth 10 times as much. A student who is still just counting physical objects will be completely lost unless we focus on the abstract value of the unit itself.
Section 5. Overcoming student misconceptions.
To wrap things up, let's rapid-fire myth-bust a few common classroom errors. First, like we mentioned earlier, changing estimates to get the correct answer completely ruins the process. Always provide a reasonable range instead of a winning exact number. Next up, visual tricks easily fool students. They very often think longer rays mean a larger angle. We have to explicitly teach that ray length does not affect the angle's measurement at all. And lastly, confusing area with perimeter. We have to reinforce that they are totally separate attributes. Area is tiling the inside, perimeter is like wrapping a string around the outside.
And that brings us to our final question for you. How will you shift your next measurement lesson from rote memorization to conceptual discovery? Don't just hand out rulers and standard formulas today. Let them measure with index cards. Let them actually build the layers of a prism. Empower your learners to discover the math through hands-on exploration and watch their understanding absolutely transform. Thanks so much for joining me on this explainer.